In Chapter 12, we're going to be working on our study of statistics. I got a few vocabulary words here for us to start with. Ultimately, the definition of statistics is just collecting and organizing, analyzing, and interpreting data, as well as drawing conclusions based on that data. Ultimately, we can divide it into two different types of statistics, two main areas. One is descriptive statistics, collecting, organizing, summarizing, presenting the data. And then also inferential statistics, which is ultimately making generalizations or conclusions from the data that we collect. Okay. So we have a few more vocabulary words here on the next slide. First of all, we're going to be dealing with populations. Okay, this is going to be a set containing all the people or objects whose properties are to be described or analyzed by the data collector. Okay. And then also a sample, which would be a subset or a subgroup of that population. So, for example, if we talk about all the people in the United States, if we were going to collect data regarding them, the population itself would be a very massive set. Whereas if we took a subgroup, like all the, if we took 2,000 people that were, coming out of the grocery store, then that would be a subset of our entire population, okay, which would be our sample. A sample becomes what we call a representative sample, as long as it exhibits characteristics typical of those possessed by the target population. So again, for instance, if we wanted to use the whole United States as our population, okay, we wouldn't want to pick only people that are coming out of the library, because that would not be necessarily representative of everybody in the United States, because generally not everybody goes to the library. Okay. So here's another example. This would be example of a population in a sample, a group of hotel owners in a large city. So you conduct a survey among citizens of the people to discover their opinions about casino gambling. So the population, okay, we're looking for the citizens of the city to be our population. Okay, and again, we're working on our sample here would be the group of hotel owners. We'll see that on the next slide. But ultimately, we're trying to discover opinions about the citizens of this city. That would be our population in this particular case. And the actual survey that we're going to conduct among the group of hotel owners is going to be the sample. Okay? So ultimately, part B here, the question we're going to be asked, similar to this in our work, is going to be, it is suggested that to survey all the people at the 6 largest nightclubs in the city on a Saturday night about their opinion on casino gambling. And the question is this a good idea? Okay, ultimately, no, because it's not a representative sample. Okay? The nightclub is more likely to have a positive attitude towards casino gambling than the general population. Okay. Similarly, if you were to take on the other hand, if you were to take the survey of people, say, coming out of a church on Sunday, they might have a different opinion altogether, and they might be totally against this gambling idea. So ultimately, we'd want to pick a place where we could survey people where we would get a representative sample or more random sample, maybe perhaps coming out of a grocery store, because we'll get all kinds of people that go shopping. Okay. So, as I mentioned earlier, random sampling, exactly what I just mentioned. It's selecting a sample in a way so that every element in the population has an equal chance of being selected. So, ultimately what we're going to do here, the methodology would be to identify each element in the population, assign numbers to each element in the population, randomly select the numbers, and assign elements in the population who have those numbers to the sample set. Okay. So, let's look at this next example. So which of the following would be the best way to find a random sample about how the city's citizens feel about casino gambling? So A, here we could randomly survey people who live in the oceanfront condominiums in the city. Okay. And ultimately many hotels lie in the oceanfront, and these people might object to the increased traffic and noise which may result. It also does not give each citizen of the city an equal chance. So this would not be a very good choice, because again, we're picking people who only have this characteristic of living by the ocean. Okay. Right. And part B, survey the first 200 people whose names appear in the city's telephone directory, and do not give each citizen in the city, does not give each citizen in the city an equal chance, because we're again just picking the first 200 people. Okay. C, this would be best, randomly select neighborhoods of the city and then randomly survey people within those selected neighborhoods. So if we had a whole bunch of different neighborhoods and we selected random people from each of these different neighborhoods, then we would have a better chance of getting a random sample, which ultimately would be a better representation for our particular survey. Okay, what we're going to look at next then is when we do collect this data, okay, we're going to talk about how to display the data. We're going to look at a few different things here. First one is what we call a frequency diagram, or frequency distribution for the data. And this particular data comes from the maximum yearly growth for 35 boys. So the age of maximum growth is on the left-hand side. Okay, the frequency of boys is the number of boys who were in each of these groups. And so in this particular case, again, we have all kinds of data, and notice that they're not terribly different from each other. There's a 10 all the way up to an 18. Okay, and what we're going to do in our distribution is just write how many boys are in this group. So we'd count how many 10s there are. We can see there's only one 10. We'd find the 11s. There's 1, 2 11s. We'd put that in here. There's 5 12s, and so on. And the total is there's 35 boys. This should all add up to be 35, of course. Okay, if it doesn't, then we might have missed one, so we should double check. But ultimately, this is what we call a frequency distribution. Okay, so when we have data, okay, especially if we have data where we have some repeats, there's a lot of 13s, a lot of 14s, etc. Okay, a frequency distribution would be a good way to display how many are in each group. Okay. So conclusions that we could base from that. So what are the conclusions we could draw? Okay, the maximum growth for most subjects occurred between 12 and 15. Okay. If you look back at the diagram, that's fairly easy to see because most of our boys are in that 12 to 15 group. There's a few in the outer parts, but most of the data is concentrated in the 12 to 15 group. Okay. Also, the number of boys who attain their maximum yearly growth at a given age increases until age 14 and then decreases after that. Okay, ultimately we can see that 10, 11, 12, 13, 14 gets bigger, but then once we get to 15, 16, 17, 18, it gets a little bit smaller again. So those are some trends that we can see by looking at the frequency distribution. Okay. All right. Here's another set of scores this time for a statistics test. We have 40 students whose scores are shown here. And what we can also do with a frequency distribution is there may not be very many repeats in here, and so ultimately it would be a pretty big table if we had to make one row for each of these. We'd have to have 40 rows ultimately. There might be some repeats, but we could literally have maybe 40 rows. So instead, we're going to group the frequencies into classes that are meaningful for the data. So for test data, it would make sense to do 10-point ranges in the 40s, the 50s, 60s, and so on. And so instead of, again, making 40 rows, we could make 1, 2, 3, 4, 5, 6 rows, and then write down how many scored in each of those groups. So if we take that data and we make those classes as such, okay, and count how many were in the 40s, 50s, 60s, and so on, and again, really the total should be 40 here because there were 40 tests taken. And with this we can see kind of a nice display of what our data is like, and we can make some conclusions here. So ultimately the class 40 to 49 has 40 as the lower class limit, 49 as an upper. Okay, so anything that's between 40 and 49, including those two, would be in that group, etc. Okay. Now, there are a couple of displays here that we can do also, which we call a histogram and a frequency polygon. Okay, a histogram is ultimately a bar graph with bars that touch. Can be used to visually display the data. So this is the maximum growth data that we had with the boys earlier. Okay, it's basically just making a graph out of the frequency distribution that we had. Okay, you'll notice that we have on the bottom here we have the years, the ages of the boys, and then over here we have the number of boys that were in each group. Okay, and this also gives us a visual trend that we can see where we talked about it being increasing and then decreasing. Okay, we can also see where most of the data is concentrated very easily in this visual manner. Okay, and then we can also take our histogram, and if we put a dot on each of the tops of the bars that we've created here, and then we connect them, we can make what we call a frequency polygon. Okay. And the frequency polygon also shows those similar trends that we had talked about when we looked at the data in the first place. Okay? So part of our work, we're going to be making histograms and frequency polygons. Now, there's another nice way to organize data, and that's what we call a stem and leaf plot. Okay? What we're going to do is we're going to take two parts. Okay? We're going to have a stem side and a leaf side. Okay, and again, the stem side consists of the tens digits, and the leaf side consists of the units digit, which is going to be the ones digit, if you will. Okay, that's really useful when we have two-digit data like this one. Okay, and this also helps us organize this data. It not only puts it in an order for us, but it also helps us see some trends. So remember, this was the data that we had from the test. Okay, so if we were to draw a stem and leaf plot for these data, okay, we had earlier, remember we had 40s, 50s, 60s, 70s, 80s, and 90s. So what we're going to do is we're going to take the tens digit and write those as our stems, okay? And then our leaves are going to be in this row over here. Now there's a couple things that we want to make sure that we do when we make a stem and leaf plot. This is the data for the first row. Remember, we had a 47, a 57, 63, 64, and so on. And then this is a stem and leaf plot for the entire set. Okay, one thing that I would always do here with this too that's different from what you see on the slide is that for my 9, for instance, I would have 2, 3, 4, 4, and 4. Okay, when you draw your stem and leaf plot, you want to have the numbers on the leaf side in order. Okay, that way when we count, when we have, I redid this one, this would be 4, and then with a 3, 5, and 7. So ultimately, as I go down through the list, it's 43, 45, 47, 50, 54, 56, and so on, all the way up to 94. We can also not only see the minimum number that we have, we can also see the maximum number. Okay, and we can see the order of all these numbers. And we're going to do something with this later, which having it in order is going to be important. So even though we see here that they did not put it in order, okay, in this class we will put the stem and leaf plots in order as we write our leaves from left to right. Okay. Alright, last thing we're going to talk about is some deceptions and visual displays of data. We're going to see a lot of visual displays here. We could see bar graphs, line graphs, pie charts, etc. It could be just a table like this. One of the things that people do with data, and you might, if you look at USA Today, there's always some colorful graphs that they use on there that sometimes are misleading. You can check that out if you like, but we'll see some here in this class as well. But ultimately, people use graphs to distort the underlying data. A couple things that could happen is the graph on the left, this graph on the left stretches the scale on the vertical axis to create an impression of rapidly increasing poverty rate. Because if you look at the poverty rates here from 2000 to 2004, it goes from 11.3 to 12.7 approximately, which isn't a huge increase, but by spreading that out, they made it look like a pretty steep line here, okay, which kind of makes it look more drastic. When we look at the graph on the right, which again is from the same data, it compresses the scale to give an impression of slowly increasing poverty rate. Okay, we could do the opposite, that if we were trying to show that the poverty rate was not going up very fast, we could compress the x-axis and ultimately, or excuse me, the y-axis, and we could make it look like it's much flatter, and therefore it would look like way better news. Okay. So that's one deception dealing with display data. There's a couple things here that we have marked here I want you to take a look at. Things to watch for with visual displays. Is there a title that explains what is being displayed? There should always be. Are the numbers lined up with tick marks on the vertical axis that clearly indicate the scale? Has the scale been varied to create a more or less dramatic impression than shown by the data? Do too many design and cosmetic effects draw attention from or distort the data? Has the wrong impression been created about how the data are changing because equally spaced time intervals are not used on the horizontal axis? Okay. So there's some things to watch for. There's a couple more on this page. We're dealing with a bar graph. Are the bar sizes scaled proportionately in terms of the data they represent? Okay. Number 6, is there a source that indicates where the data is from? Does the data come from an entire population or just a sample? Was a random sample used, and if so, are there possible differences between what is displayed in the graph and what is occurring in the entire population? Who's presenting the visual display, and do they have a special case for or against the trend shown by the graph? Okay. So these are some things that we want to watch for anytime we're dealing with a graph that we're presented with that displays any type of data. So here's an example of some misleading data. Like this one, cosmetic effects of homes with equal heights but different frontal additions. Okay. Shadow lengths make it possible to tell if they proportionally depict the given areas. So in this case, the time intervals on the horizontal axis, notice these are not uniform. Go from 20, and then this one goes up 14. So those are not uniform. Okay, also, if you look at the numbers that we have here for the average square feet, if you were to actually find the areas of these and compare them to how much bigger this one looks than this one, okay, they're very disproportionate. So ultimately this graph is deceiving because they're making this look really drastic compared to the others. Okay, and that's something that you always want to watch out for too, and pay more attention to the actual data than the actually visible display. Okay, for our work for this section, we're going to be working with some of those types of graphs and working with different data displays, etc.